Here's the lecture over chapter 5. And we're going to look at interactions of ionizing radiation. So the process by which a neutral atom acquires a positive or negative charge is referred to as ionization. Ionizing radiations can strip electrons from atoms as they travel through media. A positive ion is an atom from which an electron has been removed. Therefore, the balance of positive and negative charges has essentially been shorted by one electron, so it's positively charged in nature. An ion pair is a combination of a positively charged ion and a negatively charged ion. So charged particles such as electrons, protons, and alpha particles are involved in the ionization or being directly ionized. They have sufficient kinetic energy to produce ionization by collision as they penetrate matter. If the energy lost by the incident particle is not sufficient to eject an electron from the atom, but is used to raise the electron to higher energy levels, then it's referred to as excitation. Indirectly ionizing radiation. We're talking about uncharged particles such as neutrons and photons, and they liberate directly ionizing particles from matter when they interact with matter. And you're looking at three different types of effects here. You're looking at a photoelectric effect, a Compton effect, and pair production. We'll go through those. So photon beam description. So we've got an X-ray beam emitted from a target or a gamma ray beam emitted from a radioactive source consists of a large number of photons. It usually has a variety of energies, and the beam of photons can be described by many terms. Fluence. The fluence of photons is going to be the quotient, the change in the number of photons that you have going through by the change in the area. So if you have, normally that's represented here by a capital Phi. So basically what you've got, the change in the number coming through divided by the change in the area. Now, for those of you that have not had calculus, this is what it is referring to. And let me go ahead and load up my tablet here. And I'll kind of give you a visual description on. So when it comes to this kind of thing, you've got, and I'm going to draw this at a little bit of an angle here. So you've got a certain amount of area here, and you have all of these particles that are making its way through. And the number of particles that make it through that particular cross-sectional area is n. So that's the number of particles or photons. In this case, I think we're referring to photons, so we'll keep it as that. And then the area that it's coming through is basically the shape here of that circle. So it's the area that we're concerned with. So we're looking here at the fluence of how does the rate of change through a small amount of area, how does that fluctuate? Does it go up? Does it go down? That change is what we're looking here, and that's going to be the fluence. So the fluence rate or the flux density is going to be the fluence per unit time. So in other words, how does this change over time? And so that's going to be the fluence rate or the flux density. So the energy fluence is going to be the quotient of basically the change in the energy because of the fluence over the change in the area, the cross-sectional area that it goes through. So this is going to be the sum of energies of all photons that are entering through whatever the sphere or circle or whatever it is of that cross-sectional area. If we have a monoenergetic beam, then the dE sub FL is just the number of photons, dN, times the energy carried by each photon. In other words, we know how many photons that are going through. We know what the energy is. We know it's all the same. So this differential little part here is just going to be with the number that are coming through times the energy that they carry. So the energy fluence rate, or energy flux density, or the intensity, is going to be the energy fluence per unit time. I know there's a lot of concepts that you've got going on here right now. So we've got fluence here at the beginning. We've got the fluence rate. We've got energy fluence, which again is a multiple of the number of particles that you have going through by their energy. So this energy fluence, now we're looking at the change of that energy fluence over time. So we're looking at this as it changes over time. So menu out of the way here if I can get it to go. All right. So we've got a 6 MV X-ray port film, and it requires 10 to the 16th X-rays over an exposure time of 2 seconds to expose a film with an area of 1500 centimeters squared. So let's assume that the average photon energy here is 2 MV, and that's not an unreasonable assumption that the average energy is about 1/3. We're going to determine the photon flux, the photon fluence, energy flux, and the energy fluence. There's a lot going on there. Okay, so the photon fluence here, we've got capital Phi, is going to be the number coming through, and we know how many X-rays that is, and we know what the cross-sectional area is. Now, this obviously comes from, the number of rays that you need to have going through. The area is going to come from this. So in order to be able to convert this to this, we have to be able to go through a certain conversion rate. And let's see if I've got enough room here on the page. I'm not exactly sure if I do. I'm going to try. All right, so let's see here. So we've got, I'm going to see if I can put it up here. So we know that 100 cm is the same as 1 meter, right? So if we take that and we square it, then what do we come up with? And I don't know if it's going to read over here or not. Ah, great, it does. Okay. So we've got 100 times 100, and that's going to be cm squared because we've got cm times cm over 1 meter squared. 100 times 100, that's 1, 2, that's going to end up with 4 zeros. And sorry that this looks this terrible, but I don't really have a lot of room. I don't want to write over what we got over there. So we got 10,000 cm cubed over 1 meter cubed. Now, we're wanting to convert that 1500 cm squared. So the 1500 cm squared, we're converting that to meters. In order to be able to do that, we have to invert what we found here, divided by 10,000 cm cubed. So when we do that, we know that those cancel. And we know this divided by 10,000, that's going to move the decimal point. Let's see, 1, 2, 3. Let's see if I cancel 2 of these. I can cancel 2 of these. So if I'm dividing by 100 now, so move 1, 2. So that's why they wrote 1.5 times 10 to the minus 1, because the decimal point actually ends up right here. And that is the same as that. So that's where that comes from. So now that we've got all of that and we do the division here, we should come up with this particular value. So, and you might be asking, what are the units up here? Well, we've got 10 to the 16th X-rays. So basically the same thing as photons here. So we come up with a fluence here of 16 or 6.7 times 10 to the 16th photons per meters cubed. So that's our photon fluence. I'm going to go ahead and clear out the rest of this. And you can see that they've also done the same kind of thing over here. I've never actually thought to do it such that you write it twice like this, but it's the same thing as what we were doing over here. So that's good. Now, what is the photon flux? Well, the photon flux in this particular case is that we're going to take the fluence and we're going to see how that changes over time. So what is the flux? The flux is going to be N divided by A, and we're going to take that and we're going to see how it changes over time, so we divide that by T. So we take our fluence and we divide it by T, and that becomes the flux. And this happens, I believe, here all over time of 2 seconds. So when we do that, this is what we come up with. The flux is going to be this number of photons divided by meters squared second. Now, the energy fluence is going to be, I want to say that is psi. It is going to be the number of photons that we have coming through, of course, divided by the area. Can't quite seem to get away from that concept, can we? So we're going to take the fluence here, and if we're looking for the energy fluence, basically we're going to take this and we're going to say, okay, if on average here we have an energy of 2 MV, basically this 6 MV beam is behaving like a 2 MV beam. And what we're going to do is we're going to multiply by the energy of a 2 MV beam, or 2 MeV in this particular case. You'll find as you go through that MV is going to mean that there is a distribution. In other words, you may be given an average of this, or you may call something a 6 MV beam, but there's actually quite a bit of distribution of energies in there. When you say 2 MeV, generally what that means is that is the energy of the beam. In other words, when we say we're going to treat with a 6 MeV electron to treat somebody, we're producing 6 MeV electrons. We're not having a distribution. With photons, it's different. We're coming up with a distribution, so that's why it's written as MV. So you may have already known that up to this point, but if you don't, now you do. So now we've taken the photon fluence and we're multiplying it by the energy. So you can see here where the symbol comes down, the phi comes down, and we're going to multiply that by the energy. And so we've got 6.7 times 10 to the 16th photons per meter squared, multiplying that by the energy. In other words, we have 2 MeV per photon, so the photons will end up canceling. And so we end up with 1.3 times 10 to the 17th MeV per meter squared. Finally, for the energy flux, we want to see how the energy fluence changes with time. And because we want to do that, we're going to take the energy fluence and we're going to divide that by time. So if you're noticing a pattern here, the flux is referring to how things change over time. The fluence is basically the activity itself. If it's photon fluence, you're looking at the number that's coming through divided by the area. If it's energy fluence, you're looking at the number multiplied by its energy going through a particular area. So the energy flux is going to be this number divided by the time in which it happens, and then we come up with this 6.7 times 10 to the 16th MeV divided by meter squared dash second. Okay, so this slide is going to be a little bit busy, and if you're just reading just from the beginning chapters up to the end, you're going to be um, missing a few concepts here. So at least that this slide is and several slides after are going to be talking about. So let's kind of wade through what the slide is discussing here, and then in later chapters, we can put together exactly what some of this means in a little bit better context. So we've got these particles that are coming in, and they're smashing into atoms into the air. Now, obviously, there's a little bit of binding energy that is going to be at issue here when these particles come smashing in. Some of the energy that is produced is enough to eject electrons from their orbits, and there may even be some kinetic energy left over after this happens. So when the electrons are ejected, you're going to end up with something called an ion pair. So the average energy of the ion pair, you're looking at about 33.85 eV per ion pair. Now, the term W here is going to stand for the quantity. It's going to stand for exactly how many pairs you end up producing. Now, on average, 2.2 atoms are going to end up excited per ion pair that's produced in air. Now, the specific ionization for alpha particles in air is going to vary somewhere between 3 to 7 times 10 to the 6th ion pairs per meter. This concept here, the LET, is going to be referred to as the linear energy transfer. And it's going to reflect exactly how much energy is going to be transferred into a material for the type of particle that is entering the material. So we're going to have a specific ionization that goes along with that, times the quantity of the pairs that are produced. So the average specific ionization is going to be somewhere here in the middle, about 4.4 times 10 to the 6th ion pairs per meter. And we're going to calculate the average linear energy transfer of alpha particles in air. So if we take the specific ionization right here, and we're going to say that for alpha particles in air, it is 4 times 10 to the 6th ion pairs per meter. We're going to go ahead and substitute that in. We know here that the average energy is going to end up being a 33.85 EV per ion pair produced. So if we're looking at the energy transfer here, we're going to end up taking what looks to be this quantity. I thought immediately here, I thought that was the number of pairs produced, but it looks like it's going to be the average energy here. So we've got the specific ionization that's plugged in. We've got the quantity here, the average energy. So basically, we know how much energy each ion pair carries. We know how many ion pairs are produced. So we can cancel the units of the ion pairs, and we're left with EV over meter. So when we do that, we end up with 1.35 times 10 to the 5th KeV, converting the EV into KeV. Obviously, there's the 1,000 difference. So you divide that by 1,000, which means you take 3 off the exponent. So you end up with 1.35 times 10 to the 5th KeV per meter. This is a concept that I think is going to get talked about more in subsequent chapters. So you would not see this in chapter 5, but it's still good information. So I wanted to let you see that. So what is the range? Well, the range is going to be dictated by whatever energy you start with divided by the linear energy transfer. In other words, how much energy is going to end up being lost as it penetrates a particular material, and that's going to tell you what the range is. So we have, let's say we want to calculate the range in air for 4 MeV alpha particles with an average LET equal to 1.35 times 10 to the 5th keV per meter. So again, these are alpha particles. We just did this computation before on the previous slide. So we're going to take 4 MeV and we're going to divide it by the linear energy transfer, and we come with 0.03 meters or 3 cm in air. Doesn't seem like a lot, even for alpha particles. That doesn't seem like it goes very far, does it? Okay, so now, what about electrons? Interactions with electrons, we could either have elastic interactions with the nuclei, or we could have inelastic interactions with nuclei. So our kinetic energy here is basically going to be whatever energy we started with minus the binding energy in order to be able to release an electron. So we've got our specific ionization here, and we're going to take that and divide. We're going to take 4,500 here, and we're going to divide it by V over C. That squared, so we end up with 4,500 divided by 0.548. Obviously, we would have to know what the velocity is of the incoming particle, 0.548. We have that squared, and we come up with 15,000 IP ionized pairs per meter. As far as this particular equation goes, this is not something that I'm not exactly sure how much it's referenced in the book. It's just something that does help us come up with a specific ionization regarding electrons. We know that their speed is roughly half the speed of light. Therefore, the number of collisions that we might have at a lower speed has to have this factor taken into consideration. Again, don't worry about where it comes from, but that's what's going on here. It's moving, roughly 55% of the speed of light. So the relativistic effects here have to be factored in, and then that's where this number comes from. So if we calculate the SI and the linear energy transfer of 0.1 eV electron in air, again, roughly moving at that particular speed, or a fraction of the speed of light, we know that the quantity of energy here produced for ion pairs is going to be 33.85 eV per ion pair. So we know approximately how many ion pairs per meter are being produced. We know what the energy is, and therefore we can produce the linear energy transfer. In other words, this is how much energy would be lost by the electron per meter. And then you can take that and put that into keV if you so wish. Okay. So we have elastic scattering by nuclei that goes on. We also have inelastic scattering that's going on by nuclei. We also, in hydrogen, when Z is equal to 1, these are special cases that we have to take into consideration. We also have backscattering, which are other things that must be taken into consideration. You can see here dependencies on the square of the atomic number coming into play. So we'll be looking at that. Here we have the inelastic type of reactions here with electrons. We have specific ionization, which is considered to be high at a particular distance here. We have a Bragg peak, so that as it goes in to a substance of a particular distance, you can see that it shoots up and peaks and then eventually just drops off. In other words, the electron either gets captured or holds some other fate. This is the type of graph that we would expect to see for these interactions. You can see here these for heavily charged particles, those are protons. H2, you can also see alpha particles. This is the kind of thing that we see. Bragg peaks, again, are things that we also see in proton therapy. So you might be suspecting there's a correlation there between that and dose. So we'll look at that eventually. Okay, so indirectly ionizing interactions, we have uncharged particles where we have neutrons coming in, we have photons coming in, and they're not the ones doing the ionizing. Rather than actually doing the ionizing, they are causing particles to do it for them. So we have high energy interactions where we have 10 MeV or greater than 10 MeV. We have fast neutron reactions for 20 keV up through 10 MeV. We have intermediate, and we also have slow, where these are considered to be more elastic. So we see some of these types of things happening in the low Z nucleus, or situations such as these. All right, getting into photon beam attenuation. We have an incident photon fluence coming through here. We have, say, a set of collimators here. And let's say that we have some kind of lattice or something like that that is going to be interrupting this photon fluence. So when the photons come through, not all of them are going to make it straight through. Not all of them are going to experience something that's going to change their path. When they do change path, we see scatter. So they're going in different directions here. This is the amount of transmitted photon fluence that's coming in. So this is how much we've got coming in, and this is how much that's transmitted. We know not all of this is going to be transmitted. The question becomes, how much? So again, say we start off here with 1,000 photons. And let's say here that we have 100 of those scattered off. So we've got 10% of it scattered off. We have 200 that ends up being attenuated for some reason, stopped somewhere here in this particular material. So we've lost 300 total as it's come through. And what reaches the detector is 700. This is what ends up being transmitted. So we had 1,000 incident, we had 700 transmitted. So if a photon interacts with an atom, it is either completely absorbed or scattered away. We have equations that try to model this particular attenuation. So the attenuation, or the intensity at any given value of x, is going to be whatever you started with times e to the minus mu sub x. This linear attenuation coefficient is what's going to tell you as to how much of this intensity is going to be frittered away with interactions. And it's something you can measure and then calibrate and put into this particular equation. So equation 5.7 is going to be identical to equation 2.1. When you're talking about radioactive decay, you're looking at exponential decay. Same type of thing going on here with the linear attenuation coefficient. It's very much analogous to the decay constant. Whoops. And you can solve this particular equation in order to be able to find what you're looking for. So you can see here, you've got a transmitted intensity, you've got the absorbed thickness. So you can see the intensity at the top, starting out with 100, and then you're looking here at wherever it intercepts 50, whenever you have 50% of the transmitted intensity. At that particular point, whatever a thickness that the fluence happens to be going through, will end up being called the half value layer. So rather than write this down as a thickness of a particular material, we can instead write this as some sort of half value unit, where we can see that things are being cut in half. And if you expect to see the beam being cut in half right here, what would you expect to see here? You would expect it to go from 50 to 25. And then as you go up to another 6, maybe you expect it to go from 25 to 12 and a half, and so on and so forth. Those same types of percentages would be hit with half value layers at 1, 2, and 3, respectively. And you can see how things are divided out here. Same thing going on here. Okay, so again, let's go back to the attenuation coefficient. Mu is going to be referred to as the linear attenuation coefficient, and it depends on the energy of the photons and the nature of the material. And since the attenuation produced by a thickness x depends on the number of electrons present in that thickness, mu depends on the density of the material. Well, that could make sense here. Now, this attenuation coefficient is going to be divided up, and it's going to be divided up into several different parts here. And what we're going to do is we're going to take this linear or this attenuation coefficient, and we're going to cut it up into several different sources as to how this gets produced. Some of it's going to be from coherent scattering. Some of it's going to be from photoelectric effect. Some of it's going to be from Compton. Some of it's going to be from pair production. The other interaction that we see down here, I believe the pair production and this PD are probably mixed up. Pair production is usually represented with pi. The PD, which is going to represent a number of other interactions, such as photonuclear and electron positron pairs and things of that sort, should be represented with this variable. So these coefficients are going to vary with energy. Usually in the diagnostic range, we're going to be looking here at photoelectric as well as the Compton scattering. The mass attenuation coefficient, what we're going to be looking at here is introducing density into the equation. And so we're taking a lot of these coefficients and we're going to end up dividing them by the density. The letter rho is what's going to be used here. Okay, so obviously this symbol is going to be equal to mu. Again, if we're looking at the diagnostic section of things, we're going to be looking here at particular values. I mean, it does depend on the energy as far as which one of these you're going to be looking for. Again, you can see all of these pretty well spelled out. X, of course, being the distance that you're going to be going into the patient, or material, I should say. So if you're taking the coefficient and you're multiplying it by X, then you have all of these units spelled out here. In order to be able to condense this somewhat, we end up dividing out the X's and the adjustment, the algebra is kind of understood here, but we usually end up with something like this. This is going to be coherent scattering. This is, of course, the photoelectric absorption. This is Compton, pair production, photo disintegration. And so by accounting with all of these things, this is what we come up with. So they are definitely stating here that pair production is going to be K and photo disintegration is going to end up being with pi. So I guess other places spell it out other ways. So there we are. Again, the mass attenuation coefficient If you divide by the density, then this is the units that you come up with, and it represents the fraction of photons removed per unit thickness. So again, here, once you start introducing rho, you can see how things change. You can see that the mass attenuation coefficient for a particular value divided by rho is going to end up being spelled out differently with the different types of reactions. And we need to be able to account for that. So I don't want to go too in depth here with that, but that's what's going on. Okay, I will go back and I will address some of the problems that have been worked out in this a little bit later, but for right now, let's continue on with some of the other material that we've got. The half value layer is going to be the thickness of an absorber required to attenuate the intensity of the beam to half of its original value. And if you remember seeing with the half-life that value of 0.693, well, guess what? It pops up here again. So you can see here how your attenuation coefficient and the half value layer sort of have a reciprocal relationship with each other. So let's take a look here at the transmitted intensity. You can see here, this is basically the same graph that we had before, where you can see the half value layers hitting at certain values, or the 2, 4, 6 centimeters, so on and so forth. And then you have the absorbed thickness over here, which should be hitting at the same percentages. So you can see the first half value layer here, the second half value layer here, and the third half value layer here for this particular beam and how it's being attenuated using millimeters of aluminum. So total attenuation is going to be absorbed plus scatter. Most of the electrons set in motion by the photons will lose their energy by inelastic collisions, so ionization and excitation with atomic electrons of the material. In other words, we're looking at something that's indirect. A few, depending on the atomic number of the material, will lose its energy by Bremsstrahlung interactions with the nuclei. The Bremsstrahlung energy is going to be radiated out of the local volume as X-rays, and it's not included in the calculation of locally absorbed energy. The energy absorption coefficient is going to be the product of the energy transfer coefficient and 1 minus G. G is going to be the fraction of the energy of secondary charged particles that is lost to Bremsstrahlung in the material. So in other words, we're going to take out the stuff that is lost to Bremsstrahlung, and then the energy coefficient is pretty much going to be whatever fraction that is subtracted out, and then we'll have the rest of it. And the mass energy absorption coefficient, and let me do this for just a second, is going to be the energy transfer coefficient divided by the density. So for most interactions involving soft tissues or other low Z material, electrons lose energy almost entirely by ionization collisions, and the Bremsstrahlung component is negligible. Therefore, we're kind of going to set those two equal to each other, because the amount that you subtract out for Bremsstrahlung is really not that much. But again, this is for soft tissues or other low Z material. That cannot be said for other types of material, middle or high Z materials. These coefficients can differ appreciably when the kinetic energies of the secondary particles are high, and the material transversed has a high atomic number. So the evaluation of energy absorbed in the tissues becomes something that's different, and predicting the biological effects of radiation start to hinge on that. So here we have the energy absorption coefficient. We have the linear attenuation coefficient. We have the average energy absorbed and the photon energy here. So the attenuation coefficient for 1 MeV photon of water is 7.1 per meter. If the energy absorption coefficient for 1 MeV photons in water is 3.1 per meter, find the average energy absorbed in water per photon interaction. So we know what this value is, we know what this value is, and we can go through, we do the division here, and let's see, it's a little easier for me to see it here. Once we have that, multiplying it by 1 MeV, since that's the energy, we come up with the energy absorbed in water is 440 keV. So the X-ray emits 10 to the 12 photons per second. We have 0.11 millimeters for the mass energy absorption coefficient. That's what this is going to be. 40 keV photons. We have our linear attenuation coefficient. We have our other coefficient here. So we're going to find the total energy in keV absorbed by the screen during half a second of exposure. So plugging all of this in, we have our initial intensity. We have all of our other coefficients here that we fill in. We know how far this is going to be going in per meter. We have here our energy attenuation coefficient. And so now we see what the total energy in keV absorbed is, or at least the number of interactions. I guess they don't go through. We've got the intensity. It doesn't look to me like okay, 40 keV photons. So if we have that number of interactions, we can take that, multiply it by the energy, and we will have the energy in keV absorbed by the screen. So the energy transfer coefficient, we have a photon that interacts with the electrons in the material, and we have part or all of its energy is going to be converted into kinetic energy of electrons. So if only part of the photon energy is given to the electron, the photon itself is scattered with reduced energy, and the scattered photon may interact again with partial or complete transfer of energy to the electrons. Photons may experience one or multiple interactions. The energy lost by the photon is converted into kinetic energy of the photons. So the photon beam is traversing a material. The fraction of photon energy transferred into kinetic energy of the charged particles per unit thickness of the absorber is given by the energy transfer coefficient. So the mass energy transfer coefficient is given by this, where we go through and divide by the density. I'll work out more of these problems in a separate video. Interaction of photons with matter. Attenuation of a photon beam by an absorbing material is caused by 5 major types of interactions. You've got coherent scattering, photoelectric, you've got Compton, you've got pair production, and there should be another one here. I don't know why they have photo disintegration or anything on that, but there we are. Coherent scattering is an electromagnetic wave passing near an electron and setting it into oscillation. The oscillating electron re-radiates the energy at the same frequency as the incident electromagnetic wave, and the scattered X-rays have the same wavelength as the incident beam, probable in high atomic number materials and low energy photons. So something like this, beam goes in, beam goes out. Photoelectric effect. It's when the photon interacts with an atom and ejects one of the orbital electrons from the atom. The entire energy of the photon is transferred to the atomic electron. So the kinetic energy of the ejected electron is equal to HV minus EB. So in other words, it's going to say, hey, I've got all of this energy, I'm going to give it to you, and the electron is bound, so it has to give up some of that in order to be able to get out of the atom. So the vacancy is created by the ejected electron, thus leaving the atom in an excited state. So the vacancy can be filled by an outer orbital electron with the emission of characteristic X-rays. The Auger electron can be emitted, and the probability of photoelectric absorption depends on the photon energy. So you got a photon coming in, comes in, gives all of its energy here. It gets out by donating the binding energy here, so it comes out with a little bit less, but it's out. This vacancy here is seen by the electrons up here. If they were to jump down, depending on what level they are, you're going to see these characteristic X-rays appear. So you're seeing the mass photoelectric attenuation coefficients in these particular instances where you're looking at a graph of the mass photoelectric attenuation coefficient. And then I believe this is, let's see, it's hard for me to see again. Whoops. There we go. And then you've got the photon energy down there. So a direct hit, the electron will travel forward and the scattered photon will travel backwards after the collision. So the electron will receive maximum energy and the scattered photon will be left with minimum energy. Compton effect. The photon interacts with an atomic electron as though it were a free electron. This type of interaction is going to happen most often between 1 MeV and 10 MeV. Free here, meaning that the binding energy of the electron is much less than the energy of the bombarding photon. The electron receives some energy from the photon and is emitted at an angle. So you've got the incident photon coming in, you've got a quote unquote free electron here. And so you have the scattered photon coming out here, of course, at an angle. And the electron escaping here. And then, I'm sorry, you've got the scattered photon coming in where only part of the energy here has been given up. And then the electron goes this way, and then the scattered photon goes that way. These angles are to be computed. If it's a grazing hit, then the electron will be emitted at right angles and the scattered photon will go in the forward direction. So a photon, well, you see that there. Energy of the incident photon must be large compared with the electron's binding energy. And it decreases with increasing photon energy. And this is going to be independent of the atomic number. And you can kind of see that here. It's, the Compton electronic coefficient here and the photon energy here. You can kind of see how that's going on there. It doesn't gradually increase here with the photon energy. With pair production, the photon interacts strongly with the electromagnetic field of an atomic nucleus and gives up all of its energy in the process of creating a pair consisting of a negative electron and a positron. The threshold energy is 1.02 MeV and the energy is converted into mass. So you've got it coming in here and then all of a sudden, boom, you have an electron and a positron created here. That is pair production. Notice you're not seeing any of the electrons here in the atom be affected by this. What you are seeing here is the creation of matter out of this. And that's kind of weird, but that's the way it is. Now, if you have a positron coming in and interacting with an electron, these two end up colliding with each other. And what happens is that you see a 0.511 MeV photon carry out this way and this way. They're in opposite directions. This is done to conserve momentum. So you've got particle, antiparticle annihilation. They come in, boom, they produce two different photons. It is literally the conversion of mass into energy. A positron combines with an electron to produce two photons. Probability of pair production increases with the atomic number. The attenuation coefficient varies with z squared per atom, z per electron, and approximately z per gram. So for a given material, the likelihood of this interaction increases as the log of the incident photon energy above threshold energy, which is what you're seeing here. This is a semi-logarithmic graph. And you're seeing as the atomic attenuation coefficient here goes up, and you're seeing here as the atomic number goes up, you're seeing a gradual increase here. Now, all of these types of interactions sum together the photoelectric effect, the coherent scattering, the Compton, and the pair production add together, then you get the total number of types of interactions. So the total mass attenuation coefficient is going to be the sum of the four individual coefficients. Adding all of these mass attenuation coefficients together, this is the kind of reactions that you see. The interactions of charged particles interact principally by ionization and excitation, and it's mediated by Coulomb forces between the electric fields of the traveling particles and electric fields of orbital electrons and nuclei of atoms in the material. The collisions between the particle and the atomic electron result in ionization and excitation of the atoms. Collisions between the particle and the nucleus result in radiative loss of energy, or Bremsstrahlung, which apparently didn't get printed. So they will suffer scattering without significant loss of energy. Electrons suffer greater multiple scattering due to their smaller mass. Heavy charged particles give rise to nuclear reactions, producing radioactive nuclides. Stopping power. The rate of kinetic energy loss per unit path length of the particle. How much energy do you lose as you go through? So S divided by P is going to be the mass, or that actually should be rho, that'll be the density. So if you take the stopping power divided by rho, that's going to be the mass stopping power. And this is going to be the density of the medium expressed in MeV centimeter squared per gram. So as the particle slows down, its rate of energy loss increases, and so does the ionization or absorbed dose in the medium. And we saw the Bragg Peak earlier. The dose deposited in water increases at first very slowly with depth, and then very sharply near the end of the range before dropping to an almost zero value. Protons and heavier charged particle beams provide an advantage in radiotherapy due to their ability to concentrate dose inside the target volume and minimum dose to normal tissues. That's what this is discussing. You can see as you make it through the skin surface and you get to the tumor location, once you have penetrated so far, you begin to see the Bragg Peak emission, and then it drops off. This is different as to say 22 MV X-rays, which will penetrate, and there will be some, you can see the sort of a maximum relative dose deposit here, and then it begins to trail off the further in you go. But you can see that you still have range there to get to that point. Now, electrons suffer multiple scattering and changes in direction to motion, and again, that's due to their small size. You don't see a Bragg peak. In water or other soft tissue, they lose energy by ionization and excitation and deposit energy absorbed dose in the medium. They can interact with the magnetic field of a nucleus and be decelerated so rapidly that part of their energy is lost as Bremsstrahlung. The rate of energy loss as a result of Bremsstrahlung increases with the increase in the energy of the electron and the atomic number of the medium. Neutron interactions. Indirectly ionizing. They interact by two processes, recoiling protons from hydrogen and recoiling heavy nuclei from other elements. They're also integral in nuclear disintegrations. Energy is going to be redistributed after the collision between the colliding particles. Energy transfer is very efficient if the colliding particles have the same mass. Neutrons lose very little energy when colliding with heavier nuclei. Most efficient absorbers are going to be wax, and lead is considered to be poor shielding for these kinds of things. Results in the emission of heavily charged particles, neutrons, and gamma rays, and give rise to about 30% of the tissue dose. So you can see the depth dose distribution here of neutrons, depending on what type of beam, cobalt 60, 50 MV, 30, 16. You can see the buildup region here, and then you can see the depth dose as it goes out. So you can see the same types of things here with the depth in the tissue. You've got 5 MeV electrons, 20 MeV electrons, 30. I don't know who produces 30 MeV electrons, but there you go. And then you can see the dose along the central axis here due to protons, which are in green. The 5 MeV, the electrons are in the dashed lines here. So electrons have they can penetrate a little bit further, but you can see these little curves here, and these are not really the kinds of things you want to treat with at depth, because you're going to end up baking whatever tissue is on this side of the tumor using the electrons. This is why protons can keep their dose and then be deposited at certain depths and still hold their penetrating power. Okay, so I will create another video here that will go through and discuss some of the problems that you saw worked in here. But I do want you to concentrate on some of the major concepts here that we've had, particularly linear attenuation coefficients, mass attenuation coefficients, concepts like the flux, fluence, and those types of things.